Welcome back to another episode of Tech Talk, where we explore the fascinating world of technology and computer science. Today, we're diving into a key concept in distributed systems called linearizability. You might have heard this term in discussions about data consistency, but what does it really mean? How does it influence our interactions with databases? And why is it so vital for modern applications? Stick with us as we unpack this topic in a clear and engaging way. Let's start with a simple scenario. Picture two clients, A and B, who are constantly checking a database to read the latest value of a variable. Meanwhile, another client, C, is busy writing a new value to that same variable. So, what can A and B expect to see when they make their read requests? If client A reads the value before client C has finished writing, A will see the old value, which we'll say is 0. But if A's read happens after C has completed the write, A will see the new value of 1, assuming the database is linearizable. This means that once a write operation is completed, all subsequent reads must reflect that new value. Now, what happens when A and B are reading while C is in the middle of writing? This is where things get a bit tricky. They might end up seeing either the old value, 0, or the new value, 1. This uncertainty can create a confusing situation where the value appears to change back and forth, which isn't ideal for a system that aims to present a single, consistent view of the data. In a linearizable system, there's a critical moment during the write operation when the value changes from 0 to 1 in an atomic manner. Once client A reads the new value, every subsequent read, whether it's from A, B, or any other client, must also return that new value. This ensures that all clients see the same data, maintaining consistency. To visualize this, imagine a timeline where each operation is marked. The sequence of reads and writes needs to form a valid order. For example, if client B reads the value after client A has already seen the new value, B must also see that new value, even if C's write operation is still in progress. We also have atomic operations like compare and set or CAS. This operation checks if the current value matches an expected one before making any changes. If it does, the system updates the value. If not, it returns an error. This is crucial for keeping things consistent when multiple clients are reading and writing at the same time. One of the standout features of linearizability is its recency guarantee. Once a new value is written, all subsequent reads must reflect that value until it's overwritten again. This helps prevent situations where a read could return an outdated value, ensuring that everyone is working with the most current data. It's important to distinguish linearizability from serializability. While both concepts deal with the order of operations, linearizability emphasizes the recency of individual reads and writes, whereas serializability ensures that transactions behave as if they were executed in a sequential order. This means that even if operations are processed concurrently, they still appear to be executed one after the other. So why is linearizability so important? Think about scenarios like leader election in distributed systems, where one node must be designated as the leader. If the process isn't linearizable, different nodes might have conflicting views on who the leader is, leading to chaos. Systems like Apache Zookeeper and etcd implement linearizable operations to effectively manage distributed locks and leader elections. Linearizability is also essential for enforcing critical constraints in applications. For example, in a banking system, it's crucial to ensure that account balances never go negative. Similarly, if two users try to create an account with the same username, linearizability ensures that only one succeeds, preventing conflicts. However, not every application requires strict linearizability. In some cases, like flight bookings, a little flexibility might be acceptable. In these scenarios, we can talk about loosely interpreted constraints, where a small delay in data consistency doesn't lead to significant issues. A fascinating aspect of linearizability is how communication plays a role in recognizing stale data. For instance, if Alice announces a sports score before Bob refreshes his page, Bob realizes his data is outdated. This highlights how timely communication is crucial in distributed systems. To wrap things up, linearization is a fundamental concept that ensures consistency in distributed systems, allowing clients to read the most current data without confusion. It's vital for maintaining order in operations, especially when multiple clients interact with shared resources. By understanding linearization, developers can create more robust and reliable systems that effectively manage concurrent operations. Thanks for joining us for this episode of Tech Talk. We hope you found our exploration of linearizability insightful. Be sure to tune in next time as we delve into more fascinating topics in the tech world. Until then, keep learning and stay curious.